Hello. I don't really see an indication of audio here, so hopefully this is recording the audio. Um, okay, so what I'm going to do here is do an example problem. It's one of the messier ones. Generally, they'll be a little simpler than this, but I wanted to show you the kind of a complicated one because one of your homework problems has a similar form to this. So what we're doing is we're graphing the fundamental cycle of a trig function, okay? And this is a general example about how to go about doing that, but we're using a particular function here. So it's 1/3 times cosine of the quantity 2x minus 3 pi over 2, okay, minus 5. That's f of x, which is the same thing as y, right? So this is the function that we want to graph. Now, when we say we're going to graph a function, what we're talking about is you have to graph the points of that function, and the points consist of a pair of values for each point, right? There's an x value and a y value for each point. So that's what we need to determine is what are those points. And then if you graph the whole function, remember the trig functions are circular functions, and they consist of smooth continuous functions. So at every possible value on the real line, there is some value for that function, right? So when you say let's graph it, that's an infinite number of points. So what we typically do is we will graph what's called the fundamental cycle of the function. Okay, and so let's stop here for just a minute and think about it. The trig functions are the circular functions. That is, they arise because of rotational motion, right? And you have 6 of them. You have sine, cosine, tangent, cotangent, secant, and cosecant. Are the circular functions, okay? So each one of those, when you talk about a fundamental cycle, you're talking about the angle of the function. So, for example, sine of theta, okay, and where theta is the angle that you're referring to, and also, I'll jump ahead here and then I'll go back, but let's focus on the trig function here. We have cosine of 2x minus 3 pi. Okay. The thing that's inside the parentheses is called the argument of the trig function. Okay. So what does that mean? Well, argument, literally, if you look up the origins of it, it means something which describes something else. And so basically, what's inside the parentheses is the argument of the function, and that serves the purpose of informing the function of what the output value is, right? We have to know, we know we're doing a cosine function, but cosine of what? Cosine of this thing. And so this argument actually is the angle. This whole thing represents the angle. And so this is the cosine of some angle theta. And here theta is equal to 2x minus 3 pi over 2. Okay, so getting back to our objective here, we want to graph this entire function here, right? Not just a cosine of theta, but this entire function. And when we say we want to graph it, that means that we want to give values of x and values of y, okay, because they're ordered pairs. You give me an x value and we input it into this function. It's the independent variable, if you will. And then that determines the value of y. So a point in the Cartesian plane is an x-coordinate and a y-coordinate. So we have to determine what y is for the various x's, okay? And that brings up the question, which x's do we choose when we're going to make this graph? Okay, so going back to what I was saying earlier about, first of all, we're going to graph a fundamental cycle rather than think about graphing this entire function, okay? Because recall that all the trig functions, they continue indefinitely in both directions, okay? In the positive and negative x direction. They go on to infinity and to negative infinity, all right? So you can't draw a picture of something that's infinitely long. So what we do is we notice that these trig functions, they go through a cycle, right? They have a regular periodic shape that repeats. And the length of that shape that repeats, the longest length of a shape that repeats indefinitely in both directions, is called the period of that function. Okay, and so what we do when we graph a function is we graph the fundamental cycle, so that's really just one period of the function, and then we recognize that that actually extends again in both directions from the endpoints of that fundamental cycle. In both directions, that pattern repeats an infinite number of times, okay? And so this fundamental cycle arises from the fact that all the trig functions are circular functions, meaning they originated with the rotary motion. And so if you start in the standard position and rotate counterclockwise on the circle, a point on the circle, around the circle, when you travel completely around the circumference of a circle back to the origin, you have traversed 2 pi radians, okay? That's the angle that you've covered in one complete revolution. And so we call that a cycle. That's one cycle, right? Because you could go around that circle any number of times in that direction. And also you could go around the circle in the opposite direction any number of times, right? And so that would correspond to when you rotate counterclockwise, that's the standard orientation. That's a positive angle. And so your thetas are considered positive when you're doing counterclockwise rotations on the unit circle. And when you do clockwise rotations, your theta is negative. But we want to graph the fundamental cycle of this trig function through one cycle, okay? And what is that cycle? Well, theta goes from 0 to 2 pi. So let me see, I think I've got here we go. Okay. So theta traverses from 0 through 2 pi radians for a fundamental cycle, right? So the domain of this function, and here the function I'm talking about now is just this cosine part of this bigger function, okay? So this cosine portion here is a function itself. And for the moment, I'm just talking about this cosine function, okay? So this argument is equal to theta. So the argument of a trig function always represents an angle. So this whole thing is theta, and we know that theta is going to extend from an angle of 0 through 2 pi radians for one full cycle, or one complete rotation, right? So that is a fundamental cycle. So the domain of this function cosine of the quantity 2x minus 3 pi over 2, the domain of that function is, actually I should put a square bracket here because it includes these endpoints, okay? 0 to 2 pi. So that's the domain of this fundamental cycle of the cosine function, okay? So now, getting back to the matter at hand, we're trying to graph, this larger, a little more complicated function here, this whole thing, right? So what do we need to do that? Well, as we said, these trig functions consist, even within just if you restrict your function to just the fundamental cycle, to just one period of the revolution, if you restrict yourself to that, if you think about it, you still have an infinite number of points, right? Because you can partition that into smaller and smaller increments, right? And it basically has to do with the precision. Let me show you what I'm talking about here. So let's say this is a sine wave, right? So this is the x-axis and the y-axis, and this is y equals sine of x, let's say, okay? So x here would be a real number that represents theta, or the angle. Well, the point is, if this is 2 pi and this is 0, this is the real line from the values 0 to 2 pi. And you can partition that line an infinite number of times, right? We can go to any level of precision. So you give me a number, 2.000 is what my x value is. Well, there's also a 2.0001 and there's a 1.999 number, right, that are very close to that. And so the question is, how many zeros do I want to go out here? If I say something is exactly 2, well, then these zeros go out forever, right? And so that represents a finer and finer increment on this line. And so there's actually, even between any 2 points on this line, there's actually an infinite number of points, right? So we're trying to graph this function. Well, we can't get values for an infinite number of points to see, what this infinite number of points will be up here. That's too tedious. Well, you can't do it if it's infinite, okay? Even if it's just a very, very large number. If we divide this into, 10,000 divisions, if we're trying to graph this real accurately, so we divide this into 10,000 divisions, that's a lot of labor to get there. So what we do is we make some approximations. We just graph a few points, and you kind of know what the general shape of the function is in that area, and then you connect the dots. You make sure that the shape is kind of true to what's going on there. Okay, so what values do you pick if you're graphing a fundamental cycle of a trig function? Well, it stands to reason that 0 suggests itself as a good value to have for some trig function, and pi would be a good value to graph, right? And 2 pi would be. And so you look at the prominent, now here this is sine x, and I realize we're not doing sine x, we're actually doing a cosine function here, okay? And we're doing a more involved function. But I'm just saying that in general, if you want to do a fundamental cycle, we know we're going to graph x values or theta values. This would be better written here, maybe sine theta, and we'll call this theta, okay? But theta values, you want to go from 0 to 2 pi. And how fine of an increment do you want? So how good of an approximation of this actual curve do we want to graph it? Well, the more points, the better, right? Because if I just graph, say, 4 points of that function, I would have maybe, if I just graph a few points of it, maybe I've got that, right? And you don't know from looking at these points necessarily that there's actually a curve that happens here, right? You might be tempted just to draw straight lines, and straight lines would not be at all an adequate representation of the behavior of what this function is. And so what you do is you plot more points, and as you plot more points, that starts to show you the curvature, right? And you get a more accurate representation of what the function is. So how many points? Okay, so for our purposes, a lot of times people will just do, sometimes they'll just do pi over 2 as the increment. So they would graph the 0 point, they would find the y value for pi over 2, they'd find a value for pi, they'd find the y value for 3 pi over 2, and then the y value for 2 pi, okay? But again, that gives you kind of this just single points here. And if you don't already know that this function has this curvature, you don't really know how to draw that. So we'll go one, if you will, one notch higher in accuracy, right? Or a little better representation without doing graphing many points to get this. So instead of using pi over 2 for an increment, we're going to use pi over 4. Okay, so we would get the value of the function at 0. We get the value of the function at pi over 4. And this would be 3 pi over 4, pi, 5 pi over 4, and 3 pi over 2, which is the same thing, right, is 6 pi over 4. And then this one would be 7 pi over 4. And 2 pi you'll recognize is the same thing as 8, let me get this right, yeah, 8 pi over 4. So you could write all these in terms of pi over 4, right? 0, pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. So they're equal increments, right? And our step size is pi over 4 radians. So this is a decent approximation to get a function over a full cycle, to have that many points. Of course, it would be better with more points, but suffice to say that this will be good enough for our purposes if we do a pi over 4 increments for our fundamental cycle, okay? So let's get back to the equation that we had. We said our domain on theta it's going to cover from 0 to 2 pi. And then I said here, depending on our desired approximation accuracy, we subdivide the 2 pi interval into an arbitrary number of equally spaced intervals. So that's, again, depending on how accurate we want to be. How true a rendition of the shape of this curve we want to make is how many points that we use to estimate it with. And we're going to go with pi over 4 is our increments, okay? Here's the progression which I showed you in that graph for sine. We're not doing sine, we're doing cosine, but it doesn't matter what the function is. We're graphing from 0 to 2 pi, and we're doing it in pi over 4 increments. So here we go from pi over 4 to 2 pi over 4, which is the same as pi over 2, to 3 pi over 4, to 4 pi over 4, which is pi, right? To 5 pi over 4, to 6 pi over 4, which is the same as 3 pi over 2, to 7 pi over 4, to 8 pi over 4, which is the same as 2 pi. So that's our increment. So our theta travels from 0 to 2 pi in pi over 4 jumps. And we're going to get the y value at each one of those points. For each one of those jumps, we'll see what y is, okay? Back to this for a moment now. So I think I may have mentioned about this is called the argument of the trig function. What's inside the parentheses is called the argument, okay? So here, and whatever the argument is, this whole thing constitutes an angle. So this defines what the angle is, okay? And we call the angle theta, and it's theta is what travels from 0 to 2 pi radians, right? The whole angle, okay? And just to help solidify this term in your mind, because you'll see it occasionally in math, it's good to understand what it means. When you're talking about the argument of a function, you're talking about the value that's passed inside the parentheses, because that defines what the value of the function is going to be. It depends on what this value is, okay? And here's a way you can write of it. You can write this. You can write that the argument of cosine theta, so the argument of this function is theta. It equals theta. So the argument of this function, cosine of the quantity 2x minus 3 pi, what's the argument of this function? It's 2x minus 3 pi over 2. Now, this is the same thing as theta, okay? It's theta written in a different form. So this whole thing is going to travel from 0 to 2 pi radians, and this whole thing is theta. It is the angle, okay? So that brings us to our next step in the process. We have, let's just make a brief table here, and we'll take theta over those pi over 4 increments until we get to 2 pi, right? And we just want to know, well, what is the cosine of theta at those values, okay? And you can get that from our wheel that we've had before, right? We start here at 0, okay? And we know the ordered pair here on the unit circle, the first value, which happens to be the x value in this xy coordinate system, this is equal, this value of this x is equal to the cosine of theta. Excuse me. So theta is 0 degrees or 360, same, well, they're different, but they occur at the same place, right? They have the same terminal point, if you will. But for 0 degrees, the cosine of 0 degrees is 1. It is the x-coordinate here. X equals 1 here. But so this first number is the cosine of theta. The second number is the y-coordinate. And we know on the unit circle, it's equal to the sine of theta, okay? But we don't care about sine of theta right now because we're graphing a function that involves cosine theta. So we can travel around this wheel, and all we have to do is look up our angle, and our first coordinate that's listed for that angle is the cosine of theta. So that this wheel makes that really nice, right? So for 0, the cosine theta is 1. Let's do our pi over 4 increment. That takes us up to here, okay? And we see that the cosine theta is square root of 2 over 2. If we travel another pi over 4 distance, that brings us to pi over 2. We see here the cosine of theta at theta equal pi over 2 radians is 0. And we continue traveling another pi over 4 from pi over 2. So this is the same as 2 pi over 4, and we travel one more pi over 4. That takes us to 3 pi over 4. And the cosine of that is negative square root of 2 over 2. And you continue the same way. The next one is here, is pi, which is 4 pi over 4, which is the same thing as pi, right? And the cosine of that is negative 1. 5 pi over 4, the cosine is again negative square root of 2 over 2. 3 pi over 2, cosine of 0. 7 pi over 4, cosine positive square root of 2 over 2. That takes us back to the origin, or 360, or 2 pi. That takes us to the completion of this cycle, and the cosine of that is 1. So I've just recorded that in this table, okay? These are the values. Let's see, did I do that? No, I put the wrong one down there. Sorry. There. Sorry about that. So here's theta going in these pi over 4 chunks around the complete revolution until it gets to 2 pi. And we just recorded what the values of cosine theta were, okay? But now remember what we're graphing when we say graph this function. Our function is not cosine theta, it's this more complicated, trying to find the paper here. Let's see. Yeah, what we're graphing is this whole thing here, okay? But we start by doing it in pieces, and we say, well, this whole thing inside here is just theta. So let's get the values for cosine theta. Well, we've got those, okay? But now, and once we have those, if we know what cosine of this angle is, we can just multiply that times 1/3, subtract 5 from it, and that gives us the y value for that theta, okay? But what we want to have to graph this function is we need to know the x value and the y, not theta and y in our graph, right? So how do we do that? We go back to what we said. Theta is the argument of the function. It's 2x minus 3 pi over 2. Okay, and so we know this. And so we're going to solve for x here. So what we do is we add 3 pi over 2 to both sides of this equation. So I've added it to this side, 2x minus 3 pi over 2 plus 3 pi over 2. But that means I also have to add it to the other side. So we have theta plus 3 pi over 2 here, right? And that gives us equals, these two cancel out, and we just have 2x. So now we've got theta plus 3 pi over 2 equals 2x. And remember, we're solving for x. So we divide both sides of this equation by 2. So we take this thing and divide it by 2. And then we divide 2x by 2, right? We divide both sides of the equation by 2. Well, the 2's are going to cancel here, and we're going to be left with theta plus 3 pi over 2, that whole quantity divided by 2 equals x, right? And then we could simplify that or rewrite it. Get this out of the way here. So we've got it to this point. I'm just rewriting it in kind of simpler terms, right? We can, so this would be theta over 2 plus 3 pi here. It would be theta over 2 plus 3 pi over 2 over 2. So all we did was separate this. We've got this is equal to theta over 2 plus 3 pi over 2, and that's all I did here, okay? But then once I have this, you can simplify this part, right? And this just becomes 3 pi over 4. So now we've got a simpler form, but we've got x. We just solved this equation for x is all we did. We rewrote this instead of theta equals something. We just rewrote this to where it's x equals some function of theta, which is theta over 2 plus 3 pi over 4. So that's what x is, okay? So now remember, we've got the values for theta already, so we can plug those values in for theta here, and that'll give us the values for x. Okay, so x, let me see if I can find the yeah. Okay, so I just took our table that we already had. We already had theta and cosine theta. We've got these values, right? And we just plugged x, right just where you can see it. We just plug in, here's the equation up here. So we plug in the various values of theta into this equation. So we plug in pi over 4 for theta. So pi over 4 divided by 2 plus 3 pi over 4, right? And when you add those two together, you get 7 pi over 8 after you simplify it, okay? So again, I said pi over 4 divided by 2 is the same thing as pi over 8, okay, plus 3 pi over 4. So we got pi over 8 plus 3 pi over 4, or pi over 8 plus 6 pi over 8, because we can multiply the top and bottom by 2 here, right? And that would give us 6 pi over 8. So we have a common denominator. So we had pi over 8 plus 6 pi over 8. That would give us 7 pi over 8. So that's the value for x when theta is pi over 4. So here's theta is pi over 4. Here's the value of x. And we just do that for each theta value. We just plug in what theta is in our equation here. That gives us the value for x. And we just record them all. Okay? And now notice we've got a little time saver here, if you will, because, okay, we have cosine theta, but we got cosine of this more complicated looking function, but we already said that theta is actually the same thing as 2x minus 3 pi. That being the case, these are actually the same values because this is the same function. It's just written a different way. We've just changed the label. Instead of labeling this angle 2x minus 3 pi over 2, it's the same angle, but it's called theta, because theta equals 2x minus 3 pi over 2. So the cosine of theta will be the same thing as the cosine of 2x minus 3 pi over 2. So that's already done for us. Once you've done this, it's just a matter of making a graph, right? Because well, there's one more step. Let me go back to the original problem. Okay, so here's the original problem. So now we've got, we have the values for x, okay, but we need the values for y. And to get the values for y, though, all we need is, you think of this as theta again, right? And we've already got what the cosine of theta is, so we plug in the different values of theta here. We multiply, and we get the cosine of that. and then we multiply times 1/3 times the cosine of whatever theta was. For each value of theta, this will generate a different cosine value, right? And you take that cosine value times 1/3 minus 5, and that gives you what y, or what this whole function is. So here, we just take the different values of theta, right, and we plug them into this function, which we just said is the same thing as this, so we've already got these values. So this is the cosine of the different values of theta here, right? So we plug this in where it says cosine of 2x minus 3 pi over 2 takes on these values in this list, okay? So we just have to multiply 1/3 times 1, because that is the cosine of 2x minus 3 pi over 2, minus 5, and that gives us this value here, negative 14/3, okay? We just do that for each one. So we have 1/3 times the cosine of pi over 4, which this is the cosine of pi over 4. So 1/3 times that cosine, minus 5, and here's the number. You just do that for each one. 1/3 times this value, minus 5, and here's the number. This one turned out to be a little messy just because of the values that I originally picked here. That's why we end up with kind of odd numbers that are kind of a pain to graph, actually. So like on your final, I'll give you numbers that work out nicer than this, so you don't have to do as much with your calculator to approximate them. Because where we got these square roots and things, you have to say this is approximately equal to this, right? Because you have many more decimal places after that. And so, but basically, these points here are the y values. And remember, we've got x here. These are the x values. So to graph the function, you just say for this x value, here is the y value, and and you just go down the list. The next x value, here's the y value, and again, here was our original function. So you plug in an x value, and that makes theta be one of those increments in our list that we've already determined. And then you can calculate 1/3 times the cosine of this theta minus 5 gives you a y value. And then you're just going to plot these pairs. Here's the x value and here's the y value. Here's the next x and the next y. Okay, and I've done that. As I said, this one was a little messy here, but that's the process. Hopefully you can see this well enough here, but it was a little bit of a pain to draw the graph, but that's the process, okay? So this is the origin here. This is x and y both equal to 0, okay? So notice all of our values, all of our y values here are negative values, right? So the function, when you come down here, you get down past minus 4.5 before you get your first point. And your first x value, going back here, at theta equals 0, x was 6 pi over 8, okay? So this is the first x value. It's at 6 pi over 8. And then if you look here, we just went in increments. The x, it turns out, just goes in increments of pi over 8, right? It increases by 1 pi over 8 each time. So that makes equidistance points on this x-axis, okay? They're all pi over 8 units. So 6 pi over 8, this next one is 7 pi over 8, 8 pi over 8, 9 pi over 8, etc. All right? And then the y value is just what we calculated here for y. And so here is the y-axis on the graph. And so these are the values, and it's not the best scale there, but that's approximately where those values hit. And you can see this shape has a general cosine shape to it. Recall that a cosine curve starts at 1, right? And then it makes this dip down and then curves back up. It has an inflection point. You don't really see that there, but I'll draw it here. Your general cosine starts at 1. The fundamental cycle for a cosine function is like that. And so this would be 2 pi and 0. And this is 1, 0, negative 1, back to 1 again. So that's kind of the shape of just a general plain Jane cosine of theta, right, for the fundamental cycle. Well, notice what our function, it has that same kind of shape. It starts out high, and it dips down and then changes its curvature a little bit. It reaches a negative peak, and then it starts up and then shifts its curvature again. And so it has the same shape as a cosine function. And that makes sense because that's what our main trig function here is. It's a cosine function. So we would expect that kind of shape. The other thing that's interesting when you look at this, you'll notice that one thing you'll notice is the period of this function. Okay, it runs from 6 pi over 8 to 14 pi over 8. So that difference is 8 pi over 8, or pi, right? So the period for this whole thing is just pi. Whereas for the plain Jane ordinary cosine function, the period is 2 pi, right? To do one complete cycle, we had to travel 2 pi. And here we get the complete cycle in 1 pi. And why is that? Well, here's the answer. It's because we have this 2 multiplied times the x. So this 2 has an effect of compressing this function in angle, okay? Or if you were doing time instead of an angle as your angular value, so to speak, it would compress this. So when you have a factor of 2 times x, the independent variable, it actually reduces your period by 1/2. Okay, it changed our period from 2 pi radians to the whole cycle now occurs in pi radians. So that's interesting to notice that. And then the other portion of this, the minus 3 pi over 2, this is responsible for what's called the phase shift, okay? So the fact that we have minus 3 pi over 2 tells us that the starting point occurs here rather than occurring at the point x equals 0, okay? It occurs at 6 pi over 8 is where the beginning point is. So this is responsible for the phase shift of theta. You could think of this even in terms of 2 different angles. You could call 2x some angle alpha, for example, and then this 3 pi over 2 would be beta. So this is the cosine of one angle minus another angle. And this second angle here is the phase shift. And the phase shift translates the function in time or in angle. It moves it, okay? And here we've moved it by 3 pi over 2 radians. Okay. This 5 here is responsible for the fact that this thing isn't centered around the y value of 0. It's centered around the 5. You'll see that's where the center of this function is in terms of the positives. Well, it's not because of the 1/3. It's not exactly 5, but the 5 is what shifts. This minus 5 is why this whole thing is shifted down the axis so far. That, and then this 1/3 compresses the height, or the vertical spread of the function, okay? Because a normal cosine function, remember, has a peak-to-peak difference, or distance, if you will, of 2, right? Because the regular cosine function, its max value is +1, but its max negative value is -1. So peak to peak, there's a difference of 2 whole units there, okay? In this function, peak to peak, it's much less than 2. So here's the peak, and then here's the other peak. Okay, so we're going from here to like here, right? And that is that's actually less than 1 unit, peak to peak distance. So we've compressed it vertically because we have this 1/3 factor here also. So the 1/3 compresses the height of the function. This -5 shifts the function down the axis. Instead of it being centered at 0, it shifts it down. This compresses the height. This compresses the period by a factor of 2, where it cuts it in half, okay? So the original period of a cosine function is 2 pi, but the period of this function is pi in terms of x, okay? X only travels through a difference of pi radians. Its total difference is pi radians, and you've done one complete cycle of this function. And then again, the -3 pi over 2 shifts this thing in time. That's why this doesn't start at the origin, at the 0 point. It starts over here, okay? I'm just trying to think if I've left anything out there. I think that's probably good enough for right now, so stay tuned for more. This one was a little tedious, but I wanted you to see a more complicated function, and we will move on. Okay, so have a great day. Thank you very much.